You know, our sun, the star that gives us life, can also throw these massive tantrums. We're talking about solar storms or coronal mass ejections that can launch billions of tons of material right at us. A direct hit could be a huge problem for our power grids, our satellites, pretty much everything we depend on. The real challenge has always been predicting where they're going and how strong they'll be. But a brand new forecasting model is giving us hope that we can finally get the early warning we so desperately need. I mean, seriously, how do you even begin to do that? A billion-ton storm, moving at 1,000,000 miles an hour? It sounds like something straight out of a sci-fi movie, right? But it's very real. And trying to predict where something like that is headed is without a doubt one of the single biggest challenges in space weather forecasting today. And that's the beast we're dealing with, coronal mass ejections, or CMEs for short. These are some of the most powerful explosions happening anywhere in our solar system. And if you want to predict their impact, you have to understand their internal magnetic structure. But that's exactly where the old models just fell apart. Sometimes they'd lose the storm completely. So, let's dig into that. What exactly was the problem? Well, for years, the main way scientists tried to simulate these things had a really fundamental flaw. Okay, the old way was called the superposition method. The best way to think about it is like this. Imagine you have a drawing of the solar wind's magnetic field. Then you take a clear plastic sheet with the CME's magnetic field drawn on it, and you just lay it on top. The simulation basically just added the two pictures together. Simple, right? Well, yeah, but it's also completely wrong. In the actual physics of space, that is not at all what happens. A CME isn't a ghost. It's a massive, physical object with its own powerful magnetic field, and it has to literally push its way through the solar system. And you can see that failure right here. On the left, that's what a CME should look like, a nice, tightly coiled magnetic structure. But look at the right. The moment the simulation starts using that old superposition method, the background magnetic field just shreds it. The structure is immediately torn apart, and your forecast becomes totally useless. Oh, and it gets even worse. If you were trying to model a weaker CME, which can still be dangerous, by the way, the simulation would often just break it completely. I mean, look at this. The magnetic structure, it just vanishes. It's gone. How are you supposed to forecast a storm that your own model says doesn't even exist anymore?
So yeah, the old way was clearly broken. But this is where a team of researchers came up with a new idea that is just so much more elegant and, actually reflects reality.
They call it the displacement method. And instead of just artificially smashing two magnetic fields together, this model does what physics says should happen. It treats the CME like a real object that has to carve a path through space. It makes the solar wind's magnetic field bend, part, and flow around the CME, kind of like water flowing around a big boulder in a stream. And this image just shows it perfectly. Look at that. The internal coiled structure of the CME is totally intact, and you can see the magnetic field lines from the solar wind draping around it, being pushed aside. This is what's supposed to happen.
All right, so let's put these two methods head to head. It really makes the difference crystal clear.
This little table says it all, doesn't it? Superposition just adds the fields together, which distorts the CME and gives you really low accuracy. Displacement, on the other hand, realistically pushes the fields aside, which preserves the CME's structure and gives you high accuracy. We're basically going from an unrealistic programming shortcut to a model that actually respects the laws of physics. And here it is, the side-by-side proof. On the left, you've got the mangled mass from the old superposition method. And on the right, that clean, coherent structure is perfectly preserved by the new displacement method. The difference is just night and day. It's the difference between a broken forecast and one we might actually be able to trust. So this is obviously a huge leap forward for the science here. But why should a better computer model matter to all of us living our lives down here on Earth? It really all boils down to one simple thing. Better simulations give us better, more reliable space weather forecasts. And in the world we live in today, that's not just important, it's absolutely critical. I mean, accurate forecasts are the only thing that stands between us and some serious problems. We're talking about protecting our power grids from getting knocked out. We're talking about the satellites that give us GPS and all our communications. This is about keeping astronauts safe on space missions and even making sure global air travel doesn't get hit with dangerous communication blackouts. And hey, don't just take my word for it. The actual researchers who developed this said it themselves. They called the displacement approach a major step forward, one that lets them study how these storms evolve and, most importantly, what kind of impact they'll have when they finally get here to Earth.
So, this brings us to the big final question. We know that a massive, potentially civilization-altering solar storm isn't a matter of if it will happen, but when. Now, with models that can finally see reality for what it is, we have a much better chance of seeing it coming. We have a better chance to prepare. The only question left is, will we be ready?